Hey everybody, it's Ripley back again. Oh goodness gracious, this is the last of the series lectures, and for many of you this is the penultimate video that you're going to have to watch. We're going to talk about Taylor and Maclaurin series. You've already dealt with Taylor series. Remember, for those of you that have had me, for those of you that are watching from other institutions, I'm going to give you the full lecture here. But for those of you that have had me, and if you recall, we did a project about Taylor series, which now we're going to deal with Maclaurin series as well, which are very simple. But Taylor and Maclaurin series come from power series. So they're still, what we're talking about is still just a power series. Okay? So recall what a power series is. It is the series, let's go as n goes from 0 to infinity, c sub n times x minus a to the n. Excuse me. And this becomes, if I'm just going to list a bunch of terms, all right? We know the first term is c sub 0 plus c1 times x minus a to the first plus c sub 2 times x minus a squared. That should be an x, by the way. I don't know what the heck that other thing was. C sub 3 x minus a cubed plus c sub 4. And you're like, Ripley, what are you doing here? Just bear with me for a sec. C sub 5 times x minus a to the fifth plus dot, dot, dot. Now, what I'm going to tell you is the purpose of today, the purpose of the Maclaurin and the Taylor series is to be able to represent any function as a series on a specific interval. Remember, we're going to have a radius and an interval of convergence, just like what we had with when we represented functions as power series before. But remember, when we represented functions as power series before, they had to be in the geometric setting, right? Remember, the geometric setting was s equaled a over 1 minus r. And I could either take a derivative to get to a function or take an integral to get to a function. Like, for example, inverse tan, right? Y equals inverse tan of x. Well, this came from 1 over 1 plus x squared, which was in this form, right? Which is in the geometric form. So I could get there. I just took the antiderivative of this to get to here, and that's how we ended up with, what was it, negative 1 to the n, x to the 2n, right? Because we know, over x to the 2n plus 1 over 2n plus 1. Because this guy right here was negative 1 to the n, x to the 2n, right? All right, so again, just a little bit of review. The problem is a lot of functions don't behave like the geometric series, or we can't get to them from a geometric series. For example, e to the x, right? If I want to represent f of x equals e to the x as a power series, as a series in general, then I'm screwed. I can't write, its derivative is itself, right? Its antiderivative is itself, and I never get, the geometric form out of that. However, what I'm about to show you is going to be magical. So what we're doing is we're going to say that any function can be written, can be written in this form. And we're going to prove that we can indeed, genuinely, write any function in this form. And I'm going to show you something. All right, you ready? Clearly, this function is centered at a. Remember, power series. This is the center at x equals a. All right? By the way, a Maclaurin series is just a Taylor series where it's always centered at x equals 0, which is funny. All right, which I'm going to show you for. We're going to do that for e to the x here in just a sec. All right, first things first. Do you agree that f of a, if I've got f of a, then I would just plug that into this, and I would get c sub 0. Right? If I were to let x equal a. Now, this can be a little bit confusing. And the reason why is because you say, wait a second, Ripley, if I let x equal a, here I get 0. I'm so sorry. But you've got to remember, you're right. I would get 0 for all of the terms that have an x minus a in them. But the first term, c sub 0, remember, when I put 0 in here, this guy just becomes a 1. So all the terms go away except for that c sub 0. All right? Now, how about f prime of x? Well, let's look close. F prime of x, that term's going to go away, and I'm going to get 1 times c sub 1 times x minus a to the 0 plus 2c sub 2 times x minus a, a to the first plus 3c sub 3 plus, times x minus a squared plus 4c sub 4 times x minus a cubed. Now you're going Ripley, you're killing me right now. Plus 5c sub 5. By the way, if you did the project and you are completely stoked on said project and you remember all of this, you can skip this part. All right? But for those of you who haven't seen it before, are at different institutions, didn't do the project, did poorly on the project, whatever, watch away. All right, do you agree that f prime of a, again, if it's got an x minus a term in it, then what happens? Well, I would get, what would I get? F prime of a. This term goes, this becomes a 1. This is equal to 1 times c sub 1. Now, I know this 1 is going to annoy you guys, but bear with me for a second. All right, let's take a second derivative. We're going to do this a few times, just so you can see what's going on. This term is a constant, so it disappears, right? This becomes 2 times 1 c sub 2 times x minus a to the 0 plus 3 times 2 c sub 3 times x minus a to the first plus 4 times 3 c sub 4 times x minus a squared plus 5 times 4 c sub 5 times x minus a cubed plus dot dot dot, which implies that f double primed at a is equal to what? Well, it's going to be 2 times 1 times c sub 2. All right, just a couple more times, I promise. I know it's annoying, but bear with me. Now we're going to do, whoops, what is that 2 there? That's f double primed of r. Yeah, whatever. F triple primed of x. Sorry about that. I hope that wasn't confusing. Now, again, this is a constant. It disappears. So I get 3 times 2 times 1 times x minus a to the 0 plus 4 times 3 times 2 c sub 4. I missed a c sub 3 over here, didn't I? Slow it down, Ripley, slow it down. This is a c sub 3. This is 4 times 3 times 2 c sub 4 times x minus a to the first plus 5 times 4 times 3 c sub 5 times x minus a squared plus dot dot dot. That goes on forever, which implies that the third derivative at a, remember plug in a, 0, plug in a, 0, plug in a, no, this is already there. This is equal to, let's see, that should be, I don't know what that was supposed to be. This is 3 times 2 times 1, c sub 3. Last one. The fourth derivative of x is equal to, this is a constant term, it disappears. This is 4 times 3 times 2 times 1, c sub 4 times x minus a to the 0 plus 5 times 4 times 3 times 2, c sub 5 times x minus a to the first plus dot 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 dot. Now remember, this is going on for good. Well, what are you noticing? That means that the fourth derivative at a is equal to 4 times 3 times 2 times 1 c sub 4. And this would go on forever. So what would the nth derivative be at a of this function? Well, you should notice at this point that this is 4 times 3 times 2 times 1. This is 3 times 2 times 1, 2 times 1, 1. And then I guess we could think of this as being, well, let's not get crazy. The nth derivative at a would be what? Well, n factorial times c sub n, which implies that c sub n is always equal to the nth derivative at a, at the center, divided by n factorial. You may say, but Ripley, what about this first one? Well, think of f of a as the 0th derivative, right? Isn't the 0th derivative just 1? So 0 to the factorial, right? Not the 0th derivative is not equal to 1. It should equal, the 0th derivative should equal 0 factorial times c sub 0. Hey, guess what 0 factorial is? It's 1. So I get exactly out what I should. This right here is the most important piece, 2 pieces of information. You're really going to memorize it as c sub n is equal to the nth derivative at a divided by n factorial. And that, ladies and gentlemen, is how a Taylor series is built. Now let's actually build one. Okay, we're actually going to do one. Let's do e to the x as promised. Now I'm not gonna go into a bunch of these. I'm not gonna give you a million, a million different versions of the same thing, but I do want to do e to the x and show you some of the ramifications. I'm going to do e to the x, and then in class we're going to do sine of x and cosine of x. I might do sine of x for you as well, just because it's fun. All right, let's do e to the x. So e to the x is going to equal, by the time I'm done, I want it to equal minus a to the n. But I'm going to do the Maclaurin series. So I don't know why that's not writing. Maclaurin series, which means a equals 0. So that means we're going to have c sub n times x to the n, okay? Because it's x minus 0. All right, here we go. So the first thing that you always do with these, and like I said, you've seen these before, is since I'm at 0, I know f of x is equal to e to the x. I know that f of 0 is equal to 1. I know that f primed of x is equal to e to the x. I know that f primed at 0 is equal to 1. Oh, isn't this delightful? I know that f double primed of x, I'm only doing one more, I promise. I'm doing it just to annoy you at this point. F double primed at 0 is equal to 1. So now all I got to do is follow the formula. The formula says that c sub n is equal to what? How did I do? Well, let's go back. What's it equal? I take the nth derivative at a and I divide it by n factorial, right? So in this case, the nth derivative at 0 is always going to be 1. So it's 1, this by the way is for n equals 0 to infinity, over n factorial times, now go back, look up here, it's just, whoops, I don't know why I went back. It's still a power series, so it's just going to be x to the n, which is exactly what e to the x is. E to the x can be written as what? Well, when n equals 0, what do I get? 1. When n equals 1, what do I get? I get x over 1 factorial. When n equals 2, what do I get? X squared over 2 factorial. When I get plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus ... Hey, guess what? Again, the fancy way of writing this is simply x to the n over n factorial as n goes from 0 to infinity, which is awesome. So what is the radius of convergence for this? Let's figure that out really quickly, because that's important. Because now I don't have, remember before we had the fancy schmancy little radius of convergence. This was only true if absolute r was less than 1 in the geometric setting or the geometric form. I don't have that with Taylor and Maclaurin series. With Taylor and Maclaurin series, I actually have to show what it is, but that's not very hard, right? We just go by the ratio test. I know the limit as n goes to infinity of the absolute value of absolute n plus 1 over n plus 1 factorial times, excuse me. Now, remember I'm dividing by a sub n, so I just flip and multiply, right? So this is times n factorial over x to the n. What do I get? Oh, again, skip a beat, or pause it, don't skip a beat. Pause a beat as n goes to infinity, and rearrange these. This is x plus, whoops, this is x to the n times x to the n, times x, that's what x to the n plus 1 is, over n plus, let's put our x down there just so they're easier to. I'm pausing a beat and forgetting why I'm pausing a beat. Over x to the n times n factorial over n plus 1 times n factorial, right? And what happens here? N factorials disappear, x to the n's disappear, and what do I end up with? Whoa, this is kind of magic, right? I end up with the limit as n goes to infinity, I don't know why my thing just did that, of x over n plus 1. Well, wait a second. If I let n go to infinity, x over n plus 1, remember x is just a constant as far as that n is concerned, is equal to 0, which is always less than 1. Always. Which is pretty awesome. Which implies what? It implies that the radius is infinity. That the interval is negative infinity to infinity. Now, that means that there's no limits on this. These guys are exactly equal to one another. E to the x is equal to x to the n, the sum of x to the n over n factorial for all real numbers. It does not matter which number, like remember before we were stuck between -1 and 1. Now, if I write this thing out, right, and I want to figure out what e to the 5th is, guess what I have to do? Plug a 5 in, and we're off to the races. I would just go 1 plus 5 plus 25 halves plus 125 sixths plus 625 24ths, blah, 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 and off we go. It is exactly the same for all reals. There's no limit, no pun intended, as to what I can use this, when I can use this series to approximate that value. That's pretty powerful, especially if you don't have something like a magical, like say, a calculator. Let's do sine. Let's do sine really quickly. All right, I am going to write f of x equals sine of x, and I'm going to do it as a power series. Now you're probably realizing, like, or not as a power series, or as a power series, but as a very specific power series referred to as a Taylor or Maclaurin series. I am going to do it as a Maclaurin series because they're always easy. And I can center it at 0. If I'm going to center sine somewhere, that's a lot of S's, if I'm going to center sine somewhere, then I'm going to center it at 0. I like 0. It works really well. The function is defined at 0. Why worry about it? Or why center it somewhere else? Okay, so you ready? Here's how we do it. F of x is equal to sine of x. So f of 0, remember this is going to be, what's it mean when I center it at 0? It means it's Maclaurin. Maclaurin series. Sometimes I'll say that as Maclaurin. I don't know why. I like to add an extra. It's like when people say realtor, it's the person who sells your house. It's like, where's that extra I coming from? It's not a realtor, it's a realtor. For goodness sakes. Anyway, so f of 0 equals 0. Dang it. F primed of x is equal to cosine of x. F primed of 0 is equal to 1. F double primed of x is equal to negative sine of x. F double primed of 0 is equal to 0. Wait, what's going on here? Third derivative of x is equal to negative cosine of x. The third derivative at 0 is equal to negative 1. Oh, this is interesting. Let's do a few more because this is getting confusing as heck. The fourth derivative is equal to sine of x. The fourth derivative at 0 is equal to 0. What the heck? The fifth derivative of x is equal to okay, now I'm starting to repeat. The fifth at 0 is equal to positive 1. Okay, one more. The sixth derivative of x equals negative sine of x, just to show you that it repeats, and we'll be going for days. I can do this for the rest of my life, and I'm going to get the same pattern, right? So what are we getting? Well, our initial value is 0. Then we get 1, okay? Then we get 0, then we get negative 1. We get 0, then we get positive 1, 0, negative 1. Hey, this thing is switching signs. So how could I write this thing up? Well, hopefully you see that the sine of x is going to equal. Now let's go real easy here. Remember, I take the nth derivative. I know that c sub n is equal to the nth derivative at a divided by n factorial. But I keep getting a 0 that's repeating itself every time I have an even value, right? The 0th produces a 0. The second derivative produces a 0. The fourth derivative produces a 0. And the sixth derivative produced a 0. So how do we mess with that? Well, think about that. Any time that I register an actual value that other than 0, what am I getting? Well, let's play. First and foremost, let's acknowledge the fact that this thing is going to change signs on us every time. So let's go negative 1 to the end. Let's, again, just start the dang thing at 0. And we'll go to infinity. Okay? So we're good there. Now I got to come up with the coefficient. Well, isn't this just x to the what? Well, if I can't just go x to the n, because remember, every other term returns a 0. And I need to start this thing at 0. So what about x to the 2n? Okay, would that do it? If I put in 0, then, oh crud, then I get a 1. I can't have that. So how do I account for only odd derivatives returning a value, a non-zero value? every time it's odd, well, hopefully you recall from any assorted and sundry sources that to create odd numbers, if I'm dealing with integer or whole number values, I can either do 2n plus 1 or 2n minus 1. All right, let's do 2n plus 1 and see what happens. Now remember, it's x minus 0 to the n, but I'm accounting for the fact that I'm kind of screwed on this, right? As far as I need to have only values that return odd numbers. Otherwise, I'm going to get zeros. And then this is going to be over, well, again, remember, this and this have to match. So this is going to be 2n plus 1 factorial. Now, I know that might be a little bit confusing, but let me slow down. Let me back up a little bit. According to our formula, remember, sine any function f of x is going to be written as, excuse me, is going to be written as, I'm going to make sure that you guys understand this so I don't freak you out. The nth derivative at a divided by n factorial times x minus a to the n. So these two things always match up, don't they, when we're building our power series. However, if I'm going to write sine of x, the way I would write it is, I would write it as 0 plus 1 over 1 factorial times x to the first plus 0. So I just accounted for, let me change my color. I just accounted for this one. Now I just accounted for that one. Now I'm going to account for this one. You ready? Let's change back to black so I don't confuse you. This is going to be minus 1 over 3 factorial times x to the third, right? So we just, remember, third derivative. These guys always match up, right? And then plus 0. Now I can think of this as 0 over 2 factorial times x squared, just like I can think of this as 0 over 4 factorial times x to the fourth, right? Now what happens? Now we add, we change signs again. So plus 1 over, what's it going to be? Well, again, it's only the odd values that return non-zero numbers. So this is going to be over 5 factorial times x to the fifth, right? Plus 0 over 6 factorial times x to the sixth. I'm not going to do that anymore. So this becomes, this becomes x, right, minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial plus ... which we are claiming is this guy. This equals the sum as n goes from 0 to infinity of negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. Let's double check it. Put an n equals 0 in. That goes to 1. This becomes an x. This becomes a 1 factorial, which is 1. Booyah, right? Put a 1 in. This becomes a negative 1, x cubed, 3 factorial. Bam. Put a 2 in. That's supposed to be a 0, by the way. Put a 2 in. I get positive 1, x to the fifth, 5 factorial. I got it. And that is sine of x. Now, one last thing that is super cool about these. We know that e to the x, let me do a little thing. We just proved that e to the x is equal to the sum of x to the n over n factorial as n goes from 0 to infinity, which is equal to 1 plus x squared over 2. I should put this over 1 factorial, 2 factorial plus x cubed over 3 factorial plus ... Well, guess what? Oh, and by the way, we knew that this was true for all reals. I'm going to leave it to you, and you will do it, by the way, down the road. I'm going to leave it to you to find the interval and the radius of convergence for this guy. Excuse me. Now, watch this. This is amazing. What if I want e to the x squared? Remember how e to the x squared was so troublesome for us? We had to use like Simpson's approximations and trapezoidal approximations and all kinds of approximations to come up with how to integrate e to the x squared because there's no analytical way to do it. Oh, but wait, maybe there is. If e to the x is this, and e to the x squared is just x squared composed, let's change colors, this is that important, with e to the x, then wherever, if e to the x equals this polynomial, then wherever I see an x, what do I simply substitute? You guessed it, x squared over 1 factorial plus x to the fourth over 2 factorial plus x to the 6th. I'm just putting an x squared in wherever I see an x over here. Over 3 factorial. What would the next one be? X to the 8th over where am I? E to the x 4 factorial plus x to the 10th over 5 factorial plus dot, dot, dot. And guess what? It's real easy to integrate this guy, which is awesome. All right, one last thing, then I will shut up. I'm done. This is the coolest stuff ever, first and foremost. Finding error bounds for things like this, getting as close as we can. Remember, we're going to talk, the very last lecture is something, excuse me, called the Lagrange error bound, where we can approximate error values for these. In other words, how far out do I have to go before I get close enough to the real value of the function? All right. In other words, how many terms do I need to have before I'm close enough so that I can say, okay, I'm within 1/1000th of the real value of e to the x squared. So like if I wanted to approximate e to the 3rd, right, squared, then I would just plug a 3 in here. Now, we don't have the ability to do that for power series, for Taylor series or Maclaurin series like e to the x squared. However, you might notice something magical here. Sine is an alternating series. And remember, with alternating series, I know that the error is always less than or equal to b sub n plus 1. Just sprinkling a little fairy dust in your ear right there to give you something to think about, which is kind of cool. But I'll shut up. We'll do a bunch of these in class. There's a ton. They're super powerful. For those of you that are taking the AP exam, they're incredibly important for the AP exam. You're definitely going to see Simpson's and Maclaurin series. All right, thank you for your time and attention. Have an absolutely fantastic day, and I'll see you in class.